Thanks everybody for coming. I hope you can hear me properly. Okay, so just to make sure you're in the right place. Wow, that sounds a bit funny. This is a presentation on a tool I've been working on for about a year or so called Mallet. It's an intercepting proxy along the lines of the burps and the zaps, etc. of the world, but aimed at protocols as well as HTTPS. It can do HTTPS and HTTP, but that's not its focus. Its purpose is to do protocols other than that as well, and to do it well. Okay, I work for a company called SensePost, the obligatory introductory marketing stuff. We have offices in South Africa. We were founded in Pretoria, and we have offices in London and in Cape Town. We build, hack, train, etc., etc. So we have any services you might want. We're 18 years old now. We've founded on the 14th of February in 2001, sorry. So as you can tell, our founders had no personal life. They were bachelors, you can see. Okay, and then I'm a researcher at SensePost, which basically means I get to play with stuff, which is awesome. All right, so why do we care about intercepting flows between applications? So those flows between applications essentially make up a fundamental of those applications. A standalone application, generally not particularly interesting. Most applications are interesting because they talk to other systems. And a large proportion of those are using HTTP and HTTPS because it's the universal firewall bypass port. You don't have to worry about getting your IT department to set up firewall rules for you because 4080 and 443 are already allowed. But in other cases, we do see that a custom protocol may be in place. For example, in gaming applications, they'll implement something custom because they don't want the overhead of an HTTP header and the rest of the request response protocol. Or else they want immediate responses. And yes, WebSockets have responded to that in a way, but for legacy applications, we'll see the use of custom protocols for messaging, for example, XMPP. We've seen for banking applications, mobile banking applications, they don't use HTTP, they'll use a socket-based protocol. And so while you may have run into those things, without the tooling and the infrastructure to actually intercept those protocols and those data flows and start tampering with them and reconstructing them after you've tampered with them, it becomes very difficult to actually attack the communications. And instead we either go, well, it's good, I couldn't do anything to it. It's SSL, what are you going to do? You end up spending days or weeks writing a custom proxy trying to get in between these data flows. And yeah, often intercepting these non-HTTP protocols is very interesting because you run into applications that may not have been properly audited. I think perhaps it's a sort of legacy kind of thing. More of the older applications are using non-HTTP or WebSockets protocols because WebSockets, face it, is actually quite easy to use, but it's more recent. So if it was available at the time that the application was being developed, then maybe people would have chosen to use that. So yeah, so what I'm going to be presenting is hopefully a tool that we've been missing for probably the last 18 years. An easy-to-use intercepting proxy, analogous to the web scarabs, the burp and the zap proxies. So this is just a quick sort of taste of what it looks like. You have this is a reasonably complicated graph that is got a TCP section on this side. It's listening on port 1080, standard SOCKS port, processing SOCKS, and then there's a pipeline that differentiates based on the port 443, it puts an HTTPS pipeline together. For port 80, it puts a HTTP pipeline together. Anything else just gets relayed. And then on the right-hand side, there is a UDP-based pipeline, which allows you to, in this case, specify where it's going to. Well, okay, let me just pause that for a second. Okay, so specify where it's going to. So demonstration, I'm using a command line tool called WSCat, talking to echowebsocket.org. Echowebsocket.org simply replays back what you send it. Very simple. When we connect directly to it, you'll see we can type in, I think I paused it. Okay, so you type in something, you send it off, and it comes back exactly as it was typed. It's not particularly interesting. This is an example of a direct connection to WebSockets.org. If we now intercept that using proxy chains, or TSOCs, or whatever you prefer to use, and we connect again, it now intercepts the connection, it's redirecting it via Mallet. We send the same text, and we get back a different response. Now it's been tampered with, altered, the text is in uppercase. Not particularly exciting, but it demonstrates that you can make these changes fairly easily. So that's an example of that side of the graph. And now a demonstration of the UDP intercept. I'm going to do a host lookup for google.com, pointing to my listener on port 1053 on my local host. And when I do that, I'm going to get results that are unexpected. Ta-da. So instead of getting results for google.com, as the question section says, I got results for sensepost.com because I had a tamper script in the pipeline that modified the DNS request, changed it from google.com to www.sensepost.com, and then reconstructed the response so that it wouldn't trigger an error in the resolver that the response was for the wrong question. Okay, so this is an example. It's a complicated pipeline. We will talk a bit more about some of the ways in which you would build up your pipeline and do that. Okay, so why is it that we've got an intercepting proxy for HTTP and HTTPS, but, you know, and there's a bunch of them, Charles, WebScarab, Burp, Zap, name them, everybody's written an intercepting HTTPS proxy. BetaCap is another example. There's lots of them. But why don't we have intercepting proxies for other protocols? I think one of the reasons is that HTTP is a relatively straightforward and simple protocol to deal with. It's stateless, which means that no matter where you are in the TCP connection, you can play a request and get a response back. It's request-response based, so the person who talks and the person who responds is well defined. So it's an easy, I'll send you something, you send me something back, and then we're done kind of thing. Yes, there are issues with HTTP. For example, the slow Loris attacks from years ago triggered things like request timeouts. So when you connect to the HTTP server and you take too long to actually interact with it, it'll disconnect you. But you don't see that. That doesn't become an issue when you're tampering with a request in Burp, because Burp abstracts that from you. You've established a TCP connection from the client to Burp. You've intercepted it, you're hanging on to that request, and your browser's just waiting for you. Your browser's not going to time out. Once Burp is, once you've told Burp to send that request, Burp will open a new socket to the server, send that request, get the answer back, and discard the socket in most cases. So you don't actually have to worry about whether the server is going to time out, disconnect you, lose your state, and then you have to try and reconstruct that state again for your next request. So HTTP is that much simpler than a lot of other protocols. And I'm excluding things like NTLM authentication and so on, which are a detail, but not insurmountable. Okay, so when you run into other protocols, you've got details such as who talks first, or is there a defined who talks first? For example, if you establish an SSH connection, or you man in the middle an SSH connection, both sides immediately send their handshake. So you can't intercept a connection from one side and then tamper with that and try and send it on to the other side, because both sides are trying to talk at the same time. It's not as simple. You've got things like, I mentioned timeouts, connection timeouts. If the message doesn't get responded to fast enough, the connection is torn down and you have to try and reestablish the state of that connection. The delimiting of the messages and the frames is a unique problem for every single protocol that you're going to encounter. You have to figure out where a message starts and where a message ends. HTTP is relatively simple because you've got your header line, your status or request line. You read until you get a blank line, that's your header. Depending on your transfer encoding and your method, you might have a body, but your body length is specified. So, these are the things that you would need to be concerned about when creating a proxy for other protocols. And so what you'll find is that most people, when they are trying to intercept an arbitrary protocol, a non-HTTP protocol, it'll be a one-off. They might use something like SOCAT with the -X option, dumping hex characters so you can see what's going on. But SOCAT, while extremely powerful, is still limited. It does SSL for you. That's fantastic. It does TCP and UDP. Wonderful. But that's about where you start running into its limitations. So we want to be able to go further than that. Here's an example of another protocol that has known vulnerabilities. This is TN3270, protocol for accessing mainframes. My colleague Dominic did a presentation using a tool called BIRP, B-I-R-P, that he wrote, where he wrapped the TN3270 client, modifying some of the messages coming in to reveal hidden fields and read-only fields, make those read-only fields writable. Now, this is something we've seen in the HTTP world from the late 90s, right? Shopping carts with hidden fields containing the price of the item. But we got to 3 or 4 years ago before somebody realized that you could do exactly the same thing with TN3270, an almost 40-year-old protocol. It's a bit ridiculous, don't you think? Okay, so there's prior work. I'm not pretending that this is a unique tool, but most of the prior work, to my mind, is either too difficult to use. You've got to set up a virtual machine, you've got to set up IP tables rules, you've got to set up routing on your host box to get the traffic into the virtual machine and back down again, and it ends up becoming quite a mess. Most of these tools are not maintained, and I'll exclude things like BetterCap, which is very actively maintained. OWASP Proxy, as the author, I can abuse it. I wrote that in 2008 and abandoned it because it didn't fit my vision of where a proxy should actually be. HatKit Proxy was based on top of OWASP Proxy, actually made a user interface for it, but again was abandoned 8 years ago. Intrepidus Group's Mallory, an early implementation, 2010, again, abandoned in 2012, I guess because of lack of use or, well, ultimately, I guess, lack of interest in it. And I'm guessing that's because it is too difficult to use, very difficult to get set up and working. And a whole bunch of others that, that have attempted to solve the problem, but I think fallen by the wayside. And as I say, I'm excluding BetterCap because its focus is very specifically on HTTP and sort of transport layer issues, networking level issues. And I don't think it's actually really aiming for arbitrary TCP interception too much. And that is very actively maintained. So what I was trying to achieve was to make it easy to use. You're not going to get adoption and interest in an application if people can't figure out how to use it. So I didn't want to require routing updates and IP tables rules. Yes, you can use those things if you need to, if you have no other option. But the first option is to make it as easy as possible. And then finally, I didn't want to reinvent the wheel. There are a number of proxies out there that support HTTP and HTTPS, even these other intercepting TCP proxies. Their first pass is to build an HTTP and HTTPS implementation. And then the next instance is to add maybe one or two other protocols, and then it kind of dies out, right? Which is really disappointing, and I wanted to avoid that problem by having access to a large body of existing protocol decoders. Nobody wants to write their own gzip decoder. Nobody wants to write their own SSL implementations. Nobody wants to do the HTTP stuff, fine. So let's make use of an existing library that actually has a whole lot of protocol decoders already built in, as well as documentation. Nobody has to learn a new programming paradigm in order to actually make use of the proxy. So as I was saying, I was trying to write OWASP proxy 10 years ago, and I abandoned it because the programming model was a disaster. There were objects wrapping an object, and it was impossible to make it dynamic enough to intercept the variety of things that I wanted to be able to do. And then I ran into the Netty project. So Netty is a mature framework. Trustin Lee has been working on it and variants of it since about 2002. So he's been building this over a long time. It's not something that I just came up with in sort of 10 minutes kind of thing. It's like, yeah, that'll work, no problem. It's asynchronous, which is nice, and it's high performance. Designed with the experiences learned from an extensive amount of protocol implementation. So Netty supports a variety of different transports, TCP, UDP obviously, but it can also run over a serial connection, which makes things interesting if you're trying to intercept communications between an IoT device, for example. You could probably build a Bluetooth transport. So these are not things that exist at the moment, but the architecture exists for you to build these transports and then make use of the surrounding framework and its protocol handlers and its architecture to actually intercept that traffic and tamper with it at your will. Just to give an idea of the sort of adoption that Netty's got, Apple uses Netty in approximately 400,000 instances, processing 10 petabytes of data a day as of 2016. So that's old news. So that's an interesting thing. It does lead to some trade-offs. So some of their objects and their protocol decoders are very focused on zero copy and that sort of thing. It's not the end of the world. And if you don't want to implement your decoders in that fashion, by all means, we're not dealing with those kinds of volumes, so you don't have to go to those kinds of extents in order to actually implement your own decoders. So I mentioned the sort of transport services on the right. You've got sockets and datagrams and whatever other transport. It can do SCTP if you ever run into that. At the bottom, you've got their extensible event model, connection established, et cetera, and then your protocol support, HTTP, WebSockets, SSL, zlib, gzip, bzip, blah, 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 all the compression algorithms, protobufs and a ton of other protocols that exist already. MQTT, SMTP, there's just tons and tons and tons of protocols. So this was great for me. It's like, wow, if I ever need to test any of these things, I can just drop those blocks into my pipelines. Okay, talking about pipelines. So the way Netty is architected is this concept of a pipeline. Data comes in from the network, hits the first inbound handler, gets a chance to process it, and it just passes it up the pipeline as you go. The handlers may be what's designated as an inbound and an outbound handler. So it may process only read events or incoming events, or it may process the outbound events, or both. So an example of an inbound-outbound handler might be an SSL encoder or decoder. So you've got SSL bytes coming in, it's handshaking, passing certificates backwards and forwards, so it's doing its own thing, short-circuiting the connection, and then passing clear text and receiving clear text and doing the encryption there. And then ultimately it hits the top of the pipeline, and that handler is supposed to do something with the object, whether respond to it or save the file or whatever. So this is great. It lends itself to the composability of a proxy that I've been looking for 10 years. So how do we do this? Very, very simply, we take our pipeline and we put a single handler that just bridges two pipelines. We've got an upstream pipeline and a downstream pipeline, and they can be different, or they almost in most cases will be different. You can have an HTTP pipeline on this side with an SSL on this side that takes HTTP in and emits HTTPS. So it's very flexible. You can compose your pipelines as you like. And then, of course, your relay handler, which is responsible for copying the messages across from one pipeline to the other, also puts that up in the user interface so that you can view those messages and you can intercept them and say, hang on a second, don't pass this one just yet. I want to do something to it, and then I'll pass it on when I'm ready. Yes, if you intercept a message, you run the risk of falling foul of timeouts and that sort of thing. You need to make those choices based on the protocol that you're intercepting. So if the server doesn't implement timeouts, all good, carry on. Okay, so I've been banging on about how VMs and IP tables, etc., are bad. The alternative is the SOX protocol. SOX proxies are amazing in that you can simply wrap leaving aside the wrapping, you layer a very small SOX negotiation which says, hey, please can I talk to this host on this port? And the SOX server says, sure. And then it knows where that traffic needs to go to. So instead of trying to use routing and IP tables to intercept that traffic, you can simply use your SOX proxy to do that for you. So that makes it really approachable. It's far simpler to configure a TSOX or a proxy chains instance and wrap your application. Or on Windows, there's a tool called Proxy Cap, which works beautifully for intercepting the communications from a single process or from the entire machine. All right, so this is an example of a sort of handler skeleton. You've got channel active, which, like this name suggests, is called when the connection is established. And there's a corresponding channel inactive. Channel read passes in the message that has been read, and it could be an array of bytes, or it could be something that has been pre-parsed into a Java object that you can then manipulate. Write, in the outbound handler sense, again, the message to send to the network or downstream. And then user event triggered is for notifications such as, hey, I've managed to handshake an SSL connection with this host using these parameters. As an illustration of the kind of thing that might happen in a user event. And just to give an example, sort of concrete example, my WebSockets translation of lowercase to uppercase, that's the handler that does it. That's the custom code that I had to write to translate a WebSocket packet into uppercase. And I implemented this as a Groovy script. Looks like Java, but it's Groovy. So it's dynamic. You don't have to go through a compile and reload cycle. You can iterate on that as quickly as you like. Okay, so going faster than I thought. Okay, more time for demonstrations. I'll talk more slowly. Okay, so I chickened out on doing live demos. They wouldn't allow, the KLM wouldn't allow me to bring my sacrifices onto the plane. Something about chickens on the wings, I don't know. Okay, so this example, we've got a client application and a server application. It's speaking using JSON messages on port 9999. In order to intercept it, I set up a very simple channel or simple pipeline. I reconfigured my client to talk to 9998. So it's going to connect into my socket channel on 9998, which will then specify the upstream, localhost 9999. And then it's just going to go through my intercept handler so that I can see what the traffic looks like. And then the sync is just the output. Okay, so I sent Rogan Dawes and 1972, and it received the data and said it was fine. If we now go and look at the connection details, so you'll see on this side, we've now got a list of all the connections that have been made, the TCP source and destinations, and over here we have a bunch of messages which have been seen in various directions. So we've got a bunch of byte buffers, which is Netty's wrapper around a byte array for performance reasons. And this is quite a mission because what it leads to is that we sent a JSON message, but it came through in like 15 pieces. Well, that's not particularly useful and not easy to use. So what do we want to do? We actually want to reconstruct that JSON message into a single message, or that series of byte buffs into a single message. And we can do that by looking for the starting brace, counting the number of braces that we see in between, and then when we see closing braces, we just decrement the count until we get back down to 0, dealing with quote characters and that sort of thing as well, so strings with embedded braces. So let's do that. What we've done here now is we've dropped in a JSON object decoder. So that's going to do that message framing. It's going to count the number of braces, opening braces, count the number of closing braces, and when the count hits 0, it's going to say, this is a message, pass it on. Okay, so if we send that off, again. All right, if we go back to our connections and choose the next connection, we now see that instead of those 10 messages that we had previously, we've got one outbound and one inbound. So our outbound message, you can see, has the complete JSON stanza in it. And to do that, I didn't have to do any coding. I just dropped an existing decoder. So this is the sort of the promise of the Netty framework, is that there are so many things available for you to use that in most cases, you're not actually going to have to do any coding to build up even reasonably complex pipelines. All right. So this next demonstration is going to convert those bytes into a string. I mean, you can edit a byte array. You can go and click on the individual byte elements in the editor, but it's a bit of a painful way of doing things. And if you want to delete a character, then it gets complicated. So what we're going to do instead is we're going to take a string decoder So we're going to convert that array of bytes into a UTF-8 string. Let's make it a little bit bigger. And we're going to make use of a string encoder as well, because we need to, when our intercepting relay, intercepting handler receives that string, it's going to send out the string, which then needs to be converted back to an array of bytes for Netty to write it to the network. Okay, so instead of that single byte buff, we've now got a string which we can edit, well, not in this case because it's already passed through, but if we intercepted it, we could edit that and we could tamper with that as we wanted to. Okay, so there's one more detail. If we were to edit the string, intercept the string and edit it, so we are we're going to intercept that string and change a piece of the data. For example, change Rogan to Lauren. You'll notice that there's that checksum field. Oh no, our checksum is now invalid. So the server is now going, oops, this is no good. What are we going to do about it? Well, it would probably be a good idea to put something in the pipeline that will recalculate the checksum for us. So instead of me having to manually do it as you would go into like the burp encoder and string your changes together and choose the hash, we can actually put a little script in line that's going to do it for us. And this is a common thing, right? On a banking application, I ran into a protocol that had embedded signatures. So if you wanted to tamper with it, those signatures would no longer validate. They were signed by the application. So I exported the private key from the application, wrote my own proxy, so I've done this a few times, a custom proxy that would decode the messages, allow me to tamper with it, and then on its outbound journey would recalculate the signature for me automatically. So instead of having to write the whole thing from scratch, you can focus purely on the task at hand, which is recalculating a checksum. So all I have is an object that has a field, and we need to recalculate that checksum and update the message before we send it off. So let's do that. So what we've got here now is the script, that should be further down. So we've got our object decoder, which is going to frame our message, so the braces. We've now got a script written in Groovy that is making use of the Jackson JSON libraries to decode and encode bytes to an actual JSON object. So then we can use the Java APIs to access a particular field of the JSON object and recalculate what a field should be. And we got a similar, so in this instance, we're not actually going to recalculate the checksum just yet. What we're doing here is actually parsing it as a JSON object rather than a string. So this, again, it facilitates automated processing if you want it. Once you've got this JSON object, you can now do, you can use the APIs to modify it without having to do it manually. So here we can see it's using reflection to drill down into this object to allow you to edit the fields of the object. So in this case, we can change, if we were to send it again, we can change a field. So JSON node, you can't edit because there's no property editor for that. But if you go down to a sort of fundamental or a simple object, you can change fields and you can send that on. You can either hit send or you can turn off intercept, like with burp. When you stop intercepting, everything just gets forwarded. So here the checksum again was invalid, but the server still gave us our response. Okay, so what you're seeing here is components, building blocks that you can make use of to build more complicated pipelines. And I hope that you're seeing that in all of this, you haven't had to worry about writing a TCP listener. You haven't had to worry about calling socket writes and listening for timeouts and error handling and blah, blah, blah. That stuff is all being taken care of for you by the framework. What all you have to do is focus on the details of the protocol itself. And I'm not pretending that Mallet is going to be, this thing that you run and it just intercepts everything and fireworks. You're going to have to do some work to understand the protocol. That's what you do. You don't have to worry about the rest of the stuff that you would otherwise have to re-implement every single time. You're going to take 2 days just getting the framework up and running before you can actually even start modifying a byte of the protocol itself. So we're cutting out, or the intention is to cut out that startup hurdle and make it easy for you to actually get into the deconstruction of the protocol, the reversing of the protocol, and the discovery of the vulnerabilities that may be there. All right. Okay, so what we have here finally then is our intercept handler, which we don't really care about. But more interestingly, another script handler, which has been focused on actually recalculating the checksum. So in this case, it's a simple MD5 sum of the fields concatenated together. And we're going to update the checksum field. So here we can actually just use the various APIs of the JSON node instead of having to figure out that it's the 6th quote in the string, and if the message has a quoted string, then we're buggered and we have to recalculate from the beginning. We can actually use an API where that stuff's already been done for us. Okay, so once more, we can edit our birth date, birth year, send that on, and once again, -1 years old, but the checksum is now valid. And so that is making the whole process of constructing a proxy, to my mind, it's making it it's really, really simple. You don't have to worry about the details of the surrounding stuff. What it gives you is the ability to focus on the details of the protocol, what's unique to this particular thing you're looking at. TCP service, that stuff you can write, but why should you have to? What you really want to do is just get in between those client and server and start tampering with the data. And I hope that you can see that Mallet will make that possible. Okay, so that's the sort of evolutionary process that I think you would go through in order to construct your pipelines. Let me give you an example then, or go back to that first demonstration that I did. Let's make that a bit bigger. Can't see at this distance. Come on, what has happened? Oh, work. That was not what I wanted to do. I think I said save instead of open. No, where's my demo? Oh, there we go. All right, so what we have here is just nodes that you can drag and drop from the palette. So this palette on my right or left has got the listener, the socks, handlers, etc. And you can ultimately just drag those into your graph and configure them by double-clicking on them. So in this case, we've got our server socket channel. In this instance, it's listening on port 1080, which is a standard SOCKS port. The SOCKS initializer. This bundles a bunch of handlers together. So instead of you having to drag 4 things into the pipeline, you just drag 1, because they're commonly used together. And what that does is it looks to see what the first byte of the communication is. If it's a 4, then it's SOCKS 4. If it's a 5, then it's SOCKS 5. And then it chooses the right handler. It chooses a SOCKS 4 protocol decoder or a SOCKS 5 protocol decoder, which then handles the initial SOCKS handshaking. And eventually it says, I want to connect to google.com on port 80. And what that will do is it will fire up a message that will say, user event, connect to this particular destination. The channel handler, the target-specific channel handler, has the ability to branch based on the destination. So in this case, it's matching on the IP address and the port, or if you like, the iNet socket address, using a regular expression. If it's on port 443, it's going to go down this path where it will introduce an SSL server handler. The SSL server handler is, again, a sort of, it's a custom wrapper around 2 or 3 of the NETI SSL handlers. So there's an SNI handler in there. Who's familiar with SNI? Cool. So SNI, for those who are not, is server name indicator. It's what allows companies to virtual host SSL servers on a single IP address. So when you connect to one of those servers, in the client handshake, you'll actually say who you're trying to connect to. So while you might be connecting through an IP address, you're telling the server that actually, yes, I'm looking for google.com or www.google.com, and you can get a different SSL certificate back. And as a result, what it allows us to do is automatically generate an SSL certificate for that particular site. If it's not using SNI, we can fall back and we can create a certificate based on the requested destination. So if it said, hey, I'm actually trying to connect to www.google.com and there's no SNI message in the SSL handshake, we can fall back and use that as an alternative. So much like in Burp and Zap and all the other proxies, the automatic generated SSL certificate is signed by a certificate authority that you just need to add to your client if possible. Next steps down. Yeah. And you can see sort of similarities because ultimately port 443 and port 80 are the same other than the SSL negotiation. So you'll see the sort of parallels between the handlers in those cases. So the next step after you've negotiated SSL or made a direct connection is to install an HTTP server and client codec. So a HTTP server codec decodes requests and encodes responses. So if you've got a byte array with a request coming in, it's going to decode that into a request object. And if it gets a response object going out, it's going to encode that into an array of bytes. So you need to keep in mind which way and what objects are going backwards and forwards, whether it needs to be, it's acting as a server or it's acting as a client. But you're intelligent people, right? You're going to be reverse engineering a protocol. You can figure that part out, I guess. So the Netty object model, or HTTP request model, they send out a request header and then chunks of content. So it can process streaming HTTP requests, which is cool if that's what you want to do. But in most people's cases, what you really want to do is just deal with the whole request and its body, or the whole response and its body. So the next thing you're going to do is add the HTTP object aggregator. And what that does is it just collapses those multiple objects, much like we had the JSON object decoder, collapses those multiple things into a single request or a single response. The next step here is the WebSocket server upgrade handler. Now, if you've seen a WebSocket upgrade handshake, the client sends an HTTP message, says, hey, I'd like to upgrade to WebSockets. If the server agrees and can support WebSockets, it'll send a 101 response, upgrade OK. And at that point, once the client receives it, it's going to no longer send HTTP requests, it's going to send WebSocket frames. So what we need to do here is just watch for that 101 upgrade message. So if we see a request for an upgrade, and then we subsequently get a 101, okay, we're going to do the upgrade, you just need to get out the way. What this does, pardon me, is it removes itself and it removes the HTTP codecs on the outbound message. And there's an equivalent handler looking again from the client side. We've sent our upgrade request. We've got our upgrade response. Okay, we now need to get these parts of the pipeline out of the way because we're not going to be able to parse HTTP messages anymore. And if we try, we're going to throw an exception, right? And then finally, a script handler, which is the text WebSocket frame to uppercase handler that I showed you earlier. So that was all I needed to do in order to implement tampering with that WebSocket message. Now, Burp does WebSockets, right? Has anybody tried to tamper with a WebSocket message? Doesn't do it, right? You can't. So while HTTP and HTTPS is a solved problem, now we're drilling down into protocols that aren't solved problems. And yes, you can intercept this, and you can tamper with it. You might run foul of timeouts, so you'll get the ping WebSocket frame and the pong WebSocket frames that you would need to deal with. But if you script your changes, timeouts become less of a problem, right? If you need to do manual changes, yeah, but if you script them, no problem. So just very simply, what this function is doing is it's coming in, taking the message, checking if it's a WebSocket frame, tampering with it, and then just forwarding the message on through the pipeline. That's what that context channel read call is doing. It's just forwarding that message. So you can change the message, you can construct a new message, you can drop the message, you can do whatever you like. If you don't want to send the message on, just don't call super channel read. And yeah, that takes us down to the end of the HTTP channels. This one is just to deal with sort of unexpected traffic, not 40 or not 80 or 443. That just forwards it on. You could get an array of bytes coming up in your channel handler if you want to see what's going on, but you don't necessarily want to tamper with it. And then on this side, we've got an NIO datagram channel. NIO is Java's new IO, datagram's UDP. This configuration, it's listening on localhost 1053, as you saw in the demonstration. In this case, we don't have socks in the pipeline, which means that we need to figure out where we're going to relay this connection onto, or any data that comes in. So we're using a fixed target handler. In this case, you specify the handler name, and Mallet actually just uses reflection to instantiate an instance of that class with these parameters. So we're passing it an INET socket address, 888.53. It's going to forward it on to Google's DNS server. Here we have a script handler. The script handler just instantiates a DNS decoder and DNS response encoder. So decodes DNS queries, encodes DNS responses. Then we have in this case, it's a Java class, DNS rewrite, so it's not a script. I do find it easier to develop the scripts in Java because you get syntax highlighting and autocompletion and all the blah, blah, blah. If anybody would like to contribute our syntax area implementation that will facilitate development in Mallet, I would love that. I'll hopefully get to it in due course. So the DNS rewrite simply modifies the DNS packet, the DNS request. If it goes to google.com, changes it to www.sensepost.com, and then when the response comes back, it replaces the original question into that DNS packet. So I don't actually know very much about the structure of a DNS packet. My history is in web proxies. So I know HTTP really, really well, but DNS not so much. But it was relatively straightforward with the documentation of the DNS codecs and so on that Netty created to figure out how to modify this packet in a way that it didn't trigger any errors. It may not have been quite the objective that I wanted. My original objective was to change the request for google.com to be a CNAME that you can then use for things like SSL strip and such like. But I didn't quite achieve that. And then that passes on to a datagram relay handler. Unfortunately, at this point, I haven't quite got the link between the datagram relay handler and the user interface set up, so you can't actually see those UDP packets. It's a relatively straightforward thing to do. It should probably be a couple of hours more work just to make that link up. I don't think I am going to try and intercept UDP packets, though. Given that they're connectionless, you're almost guaranteed to hit timeouts almost immediately. So I think I'm going to leave that for scripted handlers to tamper with those UDP packets, unless somebody would like to implement that. And then one last thing that's quite interesting, given that UDP is connectionless, when you have a UDP packet coming in, at some point, what you need to do in order to send it out is associate the remote socket address and IP that packet came from with an outbound connection. And then any incoming packets from that channel can get copied backwards and forwards. It's very similar to how SOCAT does it if you're doing UDP forwarding. It forks and execs a new connection. But what that does also mean is that at the end of the day, you end up with a whole lot of these UDP listening sockets waiting for more packets that may never come. And so what this does in idle state handler is it just implements a timeout. So it listens on the channel. If there are no messages passed in either direction, in this case, it's a 10-second timeout. So 0010, read timeout, write timeout, both timeout. In 10 seconds, it'll just tear down that connection again. So it sends a message, which is handled by the datagram relay handler to say, okay, tear that down. So that gives you the ability to sort of clean up after yourself and just keep the application going without wasting resources. And that is my presentation. If you have any questions, let me go back to where I was. Today. If you have any questions, I'm happy to take them. Otherwise, you can get the code on GitHub. It is public, so you can pull that immediately. I will be following up with a blog post with some more details and some sort of suggestions on how to construct these pipelines. But the details are there on the GitHub. Questions?
No questions. Are you around later if they have questions?
I'm not going anywhere, so
great.
Yeah.
Please give them applause, guys. Thanks.